In this video, we're going to talk about symmetry of equations or symmetry of graphs. So first, talking about just symmetry. The word symmetry means that two things are the same on either side of some kind of point of reflection. So there are three different kinds of symmetry we're going to talk about in graphs. There are three different places a graph can be reflected across on a coordinate grid. So the first place a graph can be reflected is across the y-axis. So in this first graph we see a parabola that looks the same on each side of that y-axis. So this is what we call y-axis symmetry. The y-axis is acting as the point of reflection here, or the line of reflection in this case. And you can see they've given some sample points on this graph. Because we are reflecting across the y-axis, the y value is staying the same for both of those points. So they have the same b value in those ordered pairs. The only thing that's changing is the sign of the x value. So in this case, that a is positive to the left of the y-axis, or sorry, to the right of the y-axis, and it's negative to the left. So this will become important later when we check for symmetry. All y-axis or all graphs that are symmetric about the y-axis can be found using these points where the y value stays the same but we change the x value, and that has to be true for a graph that is symmetric about the y-axis. Similarly, we have graphs that are symmetric about the x-axis. So now this graph has just been turned on its side, and we can see that the curve of this graph is the same on each side of the x-axis this time. So this is said to have x-axis symmetry. And similar to y-axis symmetry, this time these points still share a piece of their point in common, but this time it's the x value that they share. The x value is staying the same, so we can see they have the same a value here. But across the x-axis, now the y value is changing. Those y values are positive above the x-axis and negative below the x-axis. So we can see the only difference in the points here are the b values. So it's positive above that x-axis, negative below it. Again, this will be a way for us to check for x-axis symmetry, looking at some examples later. And then lastly, we have what we call origin symmetry. So the origin is this point in the middle of our coordinate grid at 0, 0. If a graph has origin symmetry, it is the same, or it is reflected across that origin. So we can see the same curve occurs, but diagonally from each other this time. It's not stacked on top of each other like it was with x-axis symmetry. It's not side by side the way it was in y-axis symmetry. Now that symmetry is diagonal across the origin. This is what we call origin symmetry, again reflecting across that point 0, 0. Now this time, because we are going from a curve in the first quadrant where both a and b, both x and y are positive, to a curve in the third quadrant where both x and y are negative, or both a and b are negative, this time when we check for symmetry with our ordered pairs, both the signs of x and y will change. So that is a little bit different from x-axis symmetry and y-axis symmetry, where only a sign of one of the values changed. Now both signs of both values change. It is possible that a graph does not have symmetry at all. So if we're looking at the graph for y-axis symmetry, if that parabola were shifted left or right along the x-axis, now it is no longer symmetrical about the y-axis there. Think about whatever your point of symmetry is, or line of symmetry. It's cutting the graph in half. So a parabola that sits at 0, 0, like we see here in our example, that y-axis is cutting the parabola in half. But if we shift that graph to the left, the y-axis over here is no longer cutting that parabola in half. So it is no longer symmetric about the y-axis. So we will come across some graphs that do not have any symmetry to them at all. So now we're going to go through each kind of symmetry, and we're going to talk about how we check for that symmetry. So starting with y-axis symmetry, like I mentioned before with the ordered pairs, we check to see if the equation is the same when we switch out the x values. So if we replace a positive x with a negative x, do we end up with the same equation? So they've given us a sample equation here of y equals x squared minus 4. So where we have this x here in our equation, we're going to replace that with negative x. And when we simplify this, if we still end up with the equation x squared minus 4, then this graph is symmetric about the y-axis. If it gives us a new equation different from x squared minus 4, then this graph is not symmetric about the y-axis. So let's plug negative x in. So we'll have y equals, instead of x, we're going to plug in negative x, and that's what we'll be squaring, minus 4. Now when we simplify this, negative x squared, a negative times a negative is a positive, x times x is x squared. So this is still x squared minus 4. So since this equation matches the original, then the equation y equals x squared minus 4 is symmetric about the y-axis. We can prove this the way we did just here, where we switched out the x and made it negative x, but we can also use ordered pairs to help us prove that point as well. So let's look how we would use an ordered pair to help prove that point. So they've graphed y equals x squared minus 4 for us here, and provided us with some ordered pairs on this second graph. So one of the ordered pairs we see on that graph is 3, 5. So using that same test of changing the x value from that ordered pair, and we could have chosen any of the ordered pairs on our graph. We've just chosen 3, 5 as an example. If we change the x value, so if we make it negative, when we plug negative 3 in for x and positive 5 in for y, it should give us a true statement. And again, that proves that there is symmetry about the y-axis. So let's plug those in. So I'm just going to bring it over here so that I have more space. So we're going to plug in negative 3 for x and 5 for y. So now I'll have 5 equals negative 3 squared minus 4. Negative 3 squared is a positive 9. And then 9 minus 4 is 5, so we're left with the equation 5 equals 5, which is a true statement. So since we were left with a true statement, that means this graph is symmetric about the y-axis. Graphs that are symmetric about the y-axis are also considered even functions. So as we go forward, when you start practicing and looking at some examples, you will identify both the symmetry of the function and the type of function it is. So symmetry being x-axis, y-axis, or origin symmetry, and then we'll classify it as even, odd, or neither as the type of function.